So for our final lesson here in circle geometry, we're going to be taking a look at bisectors and perpendicular bisectors at that. It's a pretty easy concept on this one. Just make sure that you don't get over-consumed by the diagrams, and you should be okay with this. So let's take a read of the question, and let's continue on with this. So radius CD bisects chord AB. So in the question, I just want to stop here and say it bisects it. And again, that word means it splits into two even sections. And you can kind of see that with our diagram that there's a tick mark over here between AE and a tick mark over here between EB. And of course, E is going to be the intersection between our chord AB and our radius CD. Chord AB measures 8 centimeters. So that's going to be across. So over here to over there, that's all 8 centimeters. And the radius is 5 centimeters. So the radius that we have here is C to D is going to be 5 centimeters. But we also have another radius, A to C is also going to be 5 centimeters. What is the length of line segment CE? Justify your solution. Okay, so there's a couple things that we can do here straight off the bat. First off, we should know that since this is a bisector, and since we have a radius connecting this bisector, we know this is going to be not only a bisector, but a perpendicular bisector. You can kind of think of this as a very similar rule of the tangency rule, where if we had a line that's tangent at D, and we extend the line to the circle, to the center, it would be a 90 degrees. It's essentially what this chord is acting as. And actually, it's kind of interesting. This chord here, AB, it's actually another name for it if it were to extend on. It's called a secant line. And a secant line hits a circle exactly two positions on the circumference. So this is something that you don't need to know in grade 9, but you might hear that word later on. And that's actually what this chord AB is. It's actually a part of a secant line. Kind of neat. Anyways, let's go ahead and let's redraw our triangle. We have C here, A here, and E over here, and I have a 90 degrees, and I know this is 5. Now, if I know this bisects, AB is bisected, then that means that equal distances have to be to the left and to the right of this midpoint of E. So we have to have that this is 4, and this is 4 centimeters. So we have 4 centimeters here. We have 5 centimeters over here. If we want CE, we could put this into Pythagorean theory. Many of you will know this is just a 5-4-3 triangle. But in case that we want to just go ahead and prove it, let's go ahead and set up our Pythagorean theory like this. Remember, 5 is always going to go opposite, so that's going to fill in our hypotenuse. And I just went ahead and solved for B right off the bat. So 25 subtract 16 is equal to B squared. This is going to be 9. And of course, what value or what number when we square it is equal to 9? 3. And there we go. That's our answer here. CE is going to be equal to, oh, you know what? I don't like that. I'm going to erase that. CE, this is a little bit better, equals 3 centimeters. Now I can box that one off. I didn't really want to box the other one there. Our justifier for our solution is that since, of course, it's a bisected segment, then we know that this is 4, and we also know that it's 90 degrees. So that's kind of part of our justification. It's in our math. And then, of course, we just use Pythagorean theory afterwards. So that kind of ends off this beginning example.